Good morning, everyone, or good afternoon, good evening, depending of where you are sitting. Welcome to our webinar. This is part 3 of 3, how to select the right filters to improve gas turbine efficiency, availability, and reliability. Please note that this webinar is recorded and will be available after the presentation. Everyone is on mute. If you have questions, you can use the chat function in your control panel. If you have any issue with the audio over internet, please know there is also a call-in number in the audio panel, so you can check that out. Our webinar today, as mentioned, is about really finding or trying to define a method that is data-driven for you to be able to select the right filter for your environment. So we will start this with a short introduction on gas turbine and how they work, and then define our problem statement. Why should we care? Why is it important? And how do you value that? And then we'll dive in the methodology. So we're really looking at a process that is repeatable and gives you to a solution that is proven and tested. And then we will look at how this has worked in the past with a few case studies. We will keep 15 minutes for questions and answer at the end of the webinar. So use your chat function as well for any question you may have. We'll do the question live, and we'll also try to answer them during the webinar through the chat function. If we haven't had a chance to answer your question during the webinar, do not worry. We'll contact you through email after the webinar. So my name is Sophie Bélanger. I'm the Global Product Manager for Camfil Power System. Been in this role about 10 years, and I'll be the one supporting our presenters with the Q&As and the question live during the webinar. Today, presenting, we have Mark van den Eyne, which is Vice President at Camfil Power System, Jeremy Wirtje, who is our Regional Manager, and we'll start the introduction with Jim Noordermeer, who's an engineering consultant, been in the power generation industry for over 40 years, sorry. Together, they combine over 70 years of experience. So please feel free to ask anything that might come to mind. And without further ado, I'll leave the stage to Jim for a short introduction.
My name is Jim Noordermeer, and I'm here to provide a brief introduction on what is a gas turbine as a lead-in to Camfil Power Systems air inlet filtration industry. So what is a land or marine-based gas turbine? Well, it's a unique suck, squeeze, burn, blow machine that was originally developed in the late 30s and early 40s that continuously and efficiently burns ambient air in the field to produce either mechanical shaft power to drive a generator for electricity generation, or mechanical shaft power for a pipeline, say gas compression, large pumping service, and or even heavy vehicle service. Thermodynamically, a gas turbine is an air-breathing Brayton cycle machine incorporating an air inlet system, or the suck section, the inlet, a large air compressor, which is the squeeze section, a fuel combustor, or a burn section, and a large expansion turbine, the blow section, all in one drivetrain. So that's it thermodynamically. Mechanically, the compressor section and the turbine section are generally physically interconnected by a shaft which runs through the middle of the combustor section. And the output power of the turbine, the expansion turbine, will physically drive the compressor section. The remaining turbine power that has been made will drive the load, either an electrical generator, pipeline, compressor, large pump, etc. And very important to note that gas turbines are massive air breathers. As an example, an aeroderivative 45 megawatt LM6000 swallows approximately 1 million pounds per hour of air. A larger F-class machine, the 180 megawatt heavy-duty industrials, swallows around 3.6 million pounds per hour of air. And the large GHJ class gas turbines, they're swallowing in the order of 4.4 million pounds per hour of air. Imagine what 1 pound per million, 1 ppm of some kind of contaminant does to a machine that swallows 1 million pounds per hour. In one day, 24 pounds of contaminant is potentially coming into that gas turbine. What does that ambient dust contaminant do to that gas turbine machine? Next slide. Well, it leads to the 4 enemies of gas turbine performance. Please note this was covered in the Camfil's webinar part 1, the 4 enemies of gas turbine, which is available on YouTube at the address noted there or on their website. What are the 4 enemies? Well, it's composed of either dust, sand, smoke, pollen, oil mists, soot, carbon, sulfur, sea salts, and/or moistures, all of which can lead to erosion or physical blade damage, which we can see over on the right-hand side top there, physically damaging those blades. Corrosion of the hot gas path. Some of those things will damage the gas turbine section. Plugging of the turbine cooling passage. In the middle of the middle picture, we see the intricate passages which are cast into rotating turbine blades and the stationary blades. If those plug up, the cooling of those blades is impacted. And fouling and deposition, and we see that in the lower pictures to the left, where we see physical dirt basically residing on the turbines, dramatically impacting the efficiency of the machine. Next slide. What does this lead to? Loss of gas turbine performance. We're going to give you a rough example from a 50 megawatt single shaft gas turbine. And we're going to use that 2/3, 1/3 rule of thumb, being that the compressor section, which we see over in the left-hand side of the simple graphic, the compressor section, will take approximately 2/3 of the power which the turbine is making. So let's look at the first set of data there, the as designed, new and clean machine. That compressor will take approximately 100 megawatts. The turbine makes 150 megawatts, leaving a net output of 50 megawatts. What happens to that 50 megawatt gas turbine if we have a 1% efficiency loss in both the compressor and turbine sections due to, say, inadequate control of airborne contaminants and such? Well, the first thing that happens is that the compressor, instead of needing 100 megawatts, will need 101 megawatts to do the same kind of work. The turbine itself lost 1% of efficiency, which is around 1.5 megawatts. And look where the net output has dropped from 50 megawatts to 47.5 megawatts, which amounts to a 5% net power loss on that 50 megawatt machine. And not even cataloged here is the heat rate impacts that this has and the potential for cooling passage damage. So this is a means to illustrate how important it is to have an adequate and well-designed and maintained air inlet filtration system. And with that, I'd like to hand it off to Mark.
Jim, before actually going into our problem statement and explaining a little bit which kind of optimization steps are needed for getting the right air filtration solution, we would like to start for the audience to answer a question. So we have a small poll question to answer for you. And the question here is, what do you currently use to run or select your filter solutions? Do you currently use an OEM recommendation, where OEM stands for original equipment manufacturer, so the gas turbine supplier itself? Or are you driven by an EPC recommendation, so engineering, procurement, construction company recommendation? Or are you a utility company, an oil and gas company that has written their own specifications, basically on standardized environmental assessments? Or don't you really know? Or do you think it's not applicable for you itself? Maybe a question to Jeremy. What is your experience after being 9 years in the field now and talking to end customers and OEM customers? What is the current filter selection procedure?
What Jeremy? I found out is that the OEMs will specify a minimum requirement, and that could be based on anything such as the filter efficiency, but also include things such as the hydrophobicity of the filter media, possibly the media area included into the filter construction itself, and burst strength requirements are typical in the gas turbine industry to ensure that you're not going to have any breakdown and filters getting adjusted into the turbine.
No. Yeah, I think that's it's probably going to show up also when we see the answers of our audience here today. I think yes, most likely the OEM recommendation is the most used way forward in most projects. And some companies, as we know, have created a little bit their own specifications based on some typical environmental conditions that they have described themselves to generate a more standardized specification. In the end, and that will be part of our discussion today, any of these kind of recommendation specifications most of the time are not really written to be optimal for a specific location, because there is a lot of additional aspects to consider when you define a right filter solution. So before going further, let's continue with the problem statement then. Because if we look at trying to find the right solution for a gas turbine application, it is actually a balancing act that needs to take place between the original equipment manufacturer and the end user. They both have a little bit of different perspective. An OEM perspective is that, okay, they will assess what are the physical limitations, what are the physical constraints that I need to consider for the gas turbine I'm going to supply. And of course, the focus mainly from them is optimizing their own capital expenditure, because they want to sell their engine to the end user. But if you look from an end user perspective, of course, the focus should be on the overall performance of the plant, whether it's a power plant or whether it's an offshore platform or whether it's a gas compressor station. In that case, of course, when you look at performance, you need to consider both the OPEX and the CAPEX, and you really need to find the right balance between CAPEX and OPEX. You don't want to overspend on the CAPEX side, and on the other side, you don't want to under invest, and with as a result that you will have huge implications on your OPEX side. So it's really a compromise that needs to be found to get the right balance. And the consequences, if you do not really get this correctly balanced, is that if you have an unbalanced solution and you have decided, okay, I'm going to go for a cheaper CAPEX solution based on some standardized equipment, you may realize that the unbalanced solution that you get is going to result in a lot of higher costs. And the costs of this unbalanced compromise could be that you have to reduce your power output, which means, of course, you have a loss of profitability of your operations. This could be either power output or also production output if you are, of course, on an offshore platform producing the gas or an LNG plant. And on the other side, if you have not the right filtration solution to protect your gas turbine in an adequate way, you also have the additional aspect that you will have the efficiency of your engine dropping, meaning that you're going to increase the heat rate of your engine to produce a certain amount of output, which means you will increase your fuel cost. And more even, if you have really inadequate filtration solutions defined based on environmental conditions, you may end up having very frequent stops on your gas turbine, needing to do frequent filter changes, needing to do offline washing. And also, eventually, if you really have a bad filtration solution, risk of hot corrosion issues, creating havoc on your turbine section could actually lead to failures. So the problem statement, in order to get really an optimized air inlet filtration, is to really understand, first of all, what is out there. When you install a gas turbine, the environment is different everywhere in the world. So you really need to understand what kind of particulates are in the environment that I'm going to install my turbine in. What do I need to protect my gas turbine from? That's the first question. Secondly, you need to understand how I'm going to operate the turbine. What is the operation mode? Based on those two facts, you need to define also for the air filtration supplier, what priorities do you set? Availability, reliability, and so on. How many intervals can you have for stops? And then, of course, a risk assessment, again, in order to get the right balance of CAPEX versus OPEX. And with that kind of information, you need to go then to the air inlet filtration experts, and they will be able, based on that information, then give you an optimal combination of the different filter classes and stages that you need to deliver the performance that you need and you require. Keep in mind that whatever solution that you will invest in the future, try to keep in mind that it needs to be a flexible system. Operating environment as well as your operation mode can change, can shift over time. And furthermore, HEPA efficiency should never be conceded on, because HEPA efficiency is critical for you as an end user to protect your gas turbine from the very first hour that you start up your gas turbine. To go into more detail of our methodology, I'll hand it over now to Jeremy, who's going to go into the different steps that we normally would propose to our customers to really make sure that you get an optimal solution. Jeremy, take it away. Thank you.
Thank you so much, Mark. Hello to everyone attending, and thank you for joining today. So we've made the strategic decision to maintain technical skill and innovation as our core competency here at Camfil. It's what our filtration engineers, data analysis, designers, optimization experts all have in common. Our job is to assist you in selecting the best solution on all levels, whether you're an end user or an EPC, OEM, working with specific companies. We're here to show you best practices. The process that we're going to walk through today consists of 4 steps. These steps are to align, model, test, and implement. The first one is align. This is done by assessing the environment and the operational conditions. Our expectations is to make that data-driven decision that provides you the optimal filtration solution. So before I get into that, we want to ask a real quick poll question, and that is, when have you analyzed your environmental conditions? Was it before the filter system was spec'd out? Was it before the gas turbine was actually installed and commissioned? Was it after an unexpected part breakdown? Or you looked at performance and you said, well, this is suboptimal, so we need to make a change. Or in the last selection is never. So what we've seen in the past is that when you have plant operators and plant engineers see that suboptimal performance, or something just isn't right, hopefully not to the point of FOD, they'll go ahead and they'll want to begin the analysis portion, and they'll want to find out what's going wrong, how can there be a better solution, what is it going to take? Is it a simple filter change out, or is it going to be a complete inlet retrofit? Would you agree with that, Mark?
Yeah, I think most of the time it's been the case, especially on the older systems, that they realized that they did not have the right filtration solution in front of their engine. And of course, technologies has evolved. Also on the filtration side, technology has evolved, so better protection is possible now on a gas turbine. So I think there's a learning process, of course, in the industry on that level as well. So let's see what the answers are from our audience here.
Yeah, those are great results. I really like seeing that people have studied up front and made good decisions on the proper filtration from the beginning.
Yeah, I'm actually a little bit surprised that the quantity of people here, 38%, said it was before the filter spec was spec'd, actually. But yeah, it's good to see that people have learned their lessons. So.
Yeah. So when looking at this timeline for the align process, we first begin with the overall big picture. Right? We want to look at the global environment, followed by the operational mode and the application of the gas turbine. And then we want to finish up with a complete localized environment and air analysis. So if we take a look at the extreme environments throughout the world, it's pretty safe to say that when designing an inlet system, one size does not always fit all. If you consider the marine and coastal environments, you have materials such as stainless steel construction, multi-stage performance, as well as focusing on salt removal to eliminate hot corrosion. When we look at the desert, very, very high levels of dust, meaning a self-cleaning pulse filter is also often followed by a high efficiency static HEPA efficient filter. In the Arctic, we'll use an anti-icing heating system or pulse system to remove the snow and ice. And then on the opposite end, in the warm and hot environments, an evap cooler or a chiller could be recommended, since cooler air has a higher density, which will lead to a higher output. So the initial step in understanding your environment would be to use something similar to this. It's a geographical map. It's a quick and easy way to see the appropriate levels of salt, sulfur, coarse dust, and snow throughout different regions of the world. So these can be evaluated separately, but they're most efficient if you look at them overlapping. So as you can see, here's a map of Africa, Middle East, and Asia. So let's look at the salt content near the west coast of Saudi Arabia. You can see the high to intermediate levels of salt range from the coast inland to about 300 kilometers. So we really need to focus on exactly what that is per the location, because if we evaluate the east end of Africa near Somalia and Ethiopia, that high to intermediate range from the coast inland is approximately 1,300 kilometers. So it's really important to evaluate at exactly the specific point that we're looking at. Another example would be to consider Nigeria. Nigeria has such extreme high and low levels. When you look at the PM 2.5 and PM 10 in August compared to January, it's anywhere between 10 to 20 times greater, depending on what month you're looking at. We can also look at the bottom right corner graph showing the temperature and relative humidity. So when you have a change in humidity, that can wreak havoc on any inlet system, causing DP spikes and unforeseen alarms and costly shutdowns. So when looking at the selection criteria, it's necessary to consider the application of the gas turbine and functionality requirements. Ask yourself, is that engine running at base, intermediate, or peak? Does the application require minimum shutdowns, such as an LNG terminal, or have a routine maintenance interval which allows for more frequent planned outages? What's the application that the engine's driving? Is it pump, compressors, generator, etc.? One other additional factor that's important to identify is the fuel quality of each region. This map here shows the sulfur levels in diesel fuel and explains why we see lower cases of hot corrosion in the North Sea when you compare other regions of the world, like the Ivory Coast or South America. When the proper filtration solution is in place, we can remove salt and eliminate damage to the turbine internals due to hot corrosion. So once we have the initial environmental overview of a specific site, the next step is to perform a localized ambient air analysis to determine what contaminants need to be removed before entering the engine. As Jim said, and I love his terminology, engines are air breathers. This analysis, whether it be short-term or long-term, can be done with different equipment such as particle counters to analyze the amounts of dust in the air, cascade impactors for the actual concentration of the particulate, or even mobile labs when you need to do a side-by-side comparison. We look at it is, if you can't model the environment in a lab, it's important to bring the lab to the environment. So I would also encourage you to keep an eye out for Camfil's newest innovative online inlet performance and predictive modeling system, which is going to be launched in September. So stay tuned for that. So in a quick summary, we use this global information as a benchmark. We know the applications gained by those specific sites, and we're going to analyze the local data in moving forward. So once we have that, we then transition to the model aspect of the methodology. So now that we have that data, the engine performance from the OEMs, filter efficiencies, you can begin to build a comparison model to design the optimal inlet solution. So as Mark said, the key to success here is that balance. It's the balance between the CapEx and the OpEx. So using a life cycle cost analysis tool is a perfect way to evaluate the indirect filter costs. And here's an example that we've done to look at 6 different solutions. And those could be anywhere from multi-stage, 2-stage, 3-stage solutions, to even add looking at pulse versus static based on the environmental conditions. The 2 examples that we have in a life cycle cost analysis is let's look at the environment. Let's look at a similar solution at part load, first at 40 micrograms per meter cubed, and then the second one below is at 20 micrograms per meter cubed. So we've cut that particulate in half. So if solution 1 is a retrofit, and you're looking at the existing solution, it has a very minimal upfront filter cost. good pressure drop, but you see that it's a lower efficient filter, so your cost of fouling is extraordinarily high. And obviously, because of that, we may have some premature outages to water wash, and that increases the cost of downtime. So by upgrading to a more efficient filter solution, you may have a higher filter cost. However, you can see that the pressure drop increase is minimal, but the cost of fouling drop is extreme. And that's where the cost saving comes to the customer. And so eliminating downtime increases reliability and so forth. So when we can show over a given period of time that we can go from a life cycle cost of 9.4 million euros down to 1.8 million euros, whatever the cost is to get to that point, your return on investment could be anywhere from 12 to 18 months. So it makes sense. If we then look at a model that deals with the operation, so we're going to take the same site conditions, but we're going to evaluate a part load versus base load. You can see that solution one has a life cycle cost of 4.8 million euro, but upgrading to a more efficient filtration system is going to bring that LCC over time down to 1.5. And then running at base load, where the cost is much greater at 16.3, the savings is also going to be much greater in reducing that life cycle cost by 9.1 million euro. So extremely important and extremely valuable, especially having those conversations when looking at the OpEx to the CapEx to do a retrofit. So the overall additional benefits to the total cost of ownership, we're going to have less fouling, right? Less fouling means more power output available. That's going to increase the revenue stream. We're going to lower the fuel consumption per megawatt hour, which increases profit. It's a greener operation. So we're doing our environmental responsibility by lowering CO2 emissions. We've got more opportunities to run the gas turbine. There's no need for offline washing throughout the year, so increased availability is extremely important. The filter life. Okay, there's no maintenance for filters. We're going to put a solution together to extend the overall cycle, which increases availability. We're going to stabilize pressure drop, so that system is going to be based on the environmental conditions such as moisture and humidity. And overall, we want to lower maintenance cost. So understanding the filter class and how filters impact the performance of gas turbines can somewhat be confusing. So there's an easy tool out there that allows you to get a life cycle cost for the final filters. I don't have much time to go into that in more detail, but you'll see that that was part 2 of our trilogy webinar. You can request the link, you can find it on YouTube, or you can visit thevaluerating.com. The third step is to validate your solution. And how are we going to do that? We're going to do that by going to the field and lab to test those recommended solutions. So the Cam Lab is a standalone trailer with 4 independent duct systems. It allows multiple solutions to be monitored side by side. It also takes ambient temperature, humidity, particle counts, DP readings, anywhere from 20 seconds intervals to 5 minutes. It's recommended to stay at site for 3 to 6 months, so we don't just get a snapshot, we get a great overview, and we look for the worst time of the year. So the most extreme conditions in the environment, we want to test that solution. We can also perform these tests in the lab as a witness test. These labs are located in Sweden, Germany, Malaysia, Canada. They include tests such as a deluge test, efficiency test, salt, pressure drop, VDI, Aramco pulse testing, hydrophobicity, wet burst test, and electron microscope testing for the fine particulate. That proper filtration system is to execute and monitor the installation and performance. This includes both an online and offline monitoring. Before commissioning or restarting the engine, it's important to inspect the tube sheets, final filter banks to confirm that there are no leaks or bypasses. And once that's done, then we continuously monitor the environment. Here in California, unfortunately, we have wildfires on more than a regular occasion. We wish they would stop. 2 years ago in 2018, we had fires throughout the entire state. But here's what's interesting. If you take a look at the graph dated July 30th, the smoke and the jet stream was carried from the San Francisco Bay Area all the way down to Utah to the Four Corners. Less than 30 days later, fires increased in the Pacific Northwest and the wind shifted. And so you can see on the bottom chart that the smoke was carried northeast up through Montana, the Dakotas, but eventually made its way even as far as Chicago. So it's important during that time, as conditions change, you know, your last outage filters may have lasted 3 to 5 years, but because of situations like this that are unforeseen, you know, it's important to get your filters tested in a lab to make sure that you can measure the efficiencies and the pressure drop of the existing filters and put a lifespan together to see when it is you need to change. Because, you know, we want to make sure that all the performance is benchmarked and it is a learning process throughout that period, and to make sure that you have the optimal length in installation. So digital plants and real-time productive online analysis showing engine health are becoming more and more popular. The same goes for inlet filtration systems. You now have the opportunity to use data to establish pressure drop trends, filter change and water wash optimizations, power output forecasting, and the overall gas turbine efficiency. So to summarize the methodology here, again, to align, model, validate, implement, you know, whether it's on new installation, you're having some issues as far as breakdown, or you're not seeing the necessary power output, could be time for a system upgrade. This is the process we recommend. We're here to help you every step of the way, and we have all the tools in the toolbox to make that happen. So to show you some examples of how we've done that in the past and the successes that we've had, I'm going to turn it back over to Mark, and he's going to share with you 2 case studies.
Jeremy, yes, to close this webinar before our question and answers, we'll run through 2 simple case studies. The first one is actually a case study where we were invited very early in the phase of a new project on an LNG power plant, LNG plant, where we were actually hired by the EPC contractor to evaluate the environment on site, on a greenfield site, to make sure that this filter solution that we were going to propose to protect the gas turbine would be the most adequate solution to deliver the performance and the requirements and needs of the end customer in the long run. So what we did here, as you can see on this picture, there was this CamLab trailer that we put on that site, on the greenfield site. We tested 4 different combinations of filters within that system, and we really tried to simulate, based on the ventilation systems that we run in there, to simulate the airflow through the filters and exactly the same airflow that they would be running on the gas turbine, and then simulate how they would operate under these typical environmental conditions on that specific site. This site had some peak levels of dust concentration up to 120 micrograms per cubic meter, which created a little bit of a higher demand also on making sure that we would guarantee the expected filter life. Because this was an LNG terminal, they wanted to have the guarantee that they could run the final filter for 5 years without any stop, and therefore be operational during those 5 years without any stop. The original OEM recommendation there was an M6F9 solution to guarantee that 5 years life. But with our test on the site, we could show that we could even deliver a system with an EPA-grade E12 filtration solution that would also allow us to have a final filter life of 5 years, and therefore also protecting the gas turbine in a much higher way, and thereby reducing the overall life cycle cost. Although including the CapEx was slightly higher, of course, the overall cost savings over the 20-year life cycle cost was up to $17 million per gas turbine. So it was very clear for the customer which solution he wanted to install on that specific site. This is a clear indication that by learning the environment before, learning the operation, the requirements from the customer way up front, and then analyzing it really in detail, you can really bring to the table the most obvious and most optimal solution from day one. And then the second example that we show is actually an example in the Gulf of Thailand, where this kind of environmental assessment, understanding the operational mode really in detail, making sure you understand the requirements of the customer very good, has not been performed up front, with as a result that the system did not fulfill the requirements of our customer, which meant that, of course, they had a lot of issues with hot corrosion. They had a short filter life, so frequent stops actually to do filter changes. They had frequent stops to do offline washing. As you can see from the top curve here, the blue is actually the compressor efficiency of that gas turbine, where you can see a very quick drop within a 3-month period. And that were therefore requiring to stop the engine and do an offline wash after the upgrade. What you can see on the bottom curve, they actually created an increased power up from day one after the upgrade. And on top of that, they doubled the filter life on this filter solution and created a very stable and very high compressor efficiency for a prolonged period of time, not needing any stops for filter washing anymore and not needing any stops for the filter changes itself. So as a result, they have much higher production capabilities and profitability rose quickly. But on the other side, of course, because they did not have done this from day one during the initial project phase, they had, of course, to invest now for a second time with the new capex to do this upgrade. And that could have been avoided from day one if they would have done the project following our methodology from the start. So this is in short 2 case studies that show the methodology that can be used both for new installations but also for parts where you have had issues. And our final poll question is for you: which of the stages do you currently perform? This could be multiple that you can answer here on the poll question itself. So feel free to answer, give your inputs there.
The thing that I think is important to clarify is when we get contacted by end users looking to upgrade an existing filter house, perhaps what they're running right now was a great solution 10-20 years ago, and that possibly at that time technology had not been as advanced. So we've come great strides in that media filtration technology today, which we're able to offer much greater solutions and achieve a higher engine performance.
I think that's a good point. I think initially, if you think about it, of course, the efficiency of the gas turbine initially was like 25 up to 30% simple cycle efficiency, where now we're talking about 40% simple cycle efficiencies. And of course, that means that the engines are more susceptible, more fragile in some way also to the environment, and as a result need better filtration. And that learning process has taken some time within the industry, I think, as well. But yeah, I agree also that technologies on the air filtration side have also evolved massively in the last 10 years, so which helps for sure. Okay, it's I think this is a nice view. So still 1 quarter does none of the above, which is of course meaning that okay, there is still some work to do for us to educate the market and make sure that they start using this kind of methodology to make sure that they have make the right decisions when they invest in new projects. But I'm happy to see that there is also 39% that have started to do this alignment process, make sure that they understand the environment and the operational assessment, and then try to model it in a concise way. So that's positive to see, at least.
So we're up for the time for the question period. We have about 15 minutes to answer your Q&A. So I guess one of the first questions we received in the chat, I'll give that to Mark. It was asked about the case study and some concern about how can E10 filter element resist the moisture. So can you talk a little bit more about key criteria in filter construction that make them appropriate for offshore environment, by example?
That's a good question. Of course, E10 or HEPA filtration, of course, focuses on stopping the particulates, dust particles up to very submicron size. But of course, when you talk about moisture and salt, especially to avoid hot corrosion, you really need to make sure that that media is also hydrophobic in the design of your filter construction. The filter element, as well as the filter house construction, is also completely airtight with a bypass-free, seal-free. So you need to make sure that your filter construction is made in a way that whatever moisture gets into your filter is evacuated as soon as possible out of your system. And if moisture would actually get onto the salt particles and create the salt to become a liquid, that at least it is drained out of your filter rather than stay into your filter and give it the time to migrate through the media over time when you have these cycles of high humidity, low humidity, of course. But there is, of course, features to be looked at both in the construction of the filter as well as on the media. It's not only the media that will do the job. You will need both.
Thank you, Mark. Question for Jeremy here. When you looked to, or you showed the life cycle cost example, you highlighted that reduction in falling typically are better than, or are worth more money than the reduction or the increase in pressure up cost. So at least in the example that you were showing, that was the case. We have someone here that had a case where Camfil recommended E11 filter instead of E12. Can you talk a little bit more about is E12 or higher efficiency always better? Is there a diminishing return, and how do we establish that for a customer?
Yeah, I think that's exactly why it's so important to understand your operational mode as well as your environment in detail. It does not mean that everywhere in the world you should put E12 to protect your gas turbine. You could have sites where the environment is actually not as highly dust loaded, or very fine dust concentrations are not that high, and therefore an E11 would probably protect your engine as good as if you would do an E12 in a very high dust loaded environment, right? So it's basically, the analysis is made in that case probably by assessing how many operating hours does the engine run, what is the current environmental dust concentration on that specific site, what has the experience shown from the past on their engine, on fouling, on power output losses, and then based on that, the recommendation probably has come out that the E11 is the best payback for that customer in specific. So it's really probably a really local assessment that has been made in this case. And
I would also like to add that it also depends on the type of gas turbine that you're running, right? Is it a light to heavy industrial gas turbine? Is it an aeroderivative gas turbine? You know, how susceptible is it to the actual pressure drop and whatnot too? So that, as Mark said, the importance of the life cycle cost analysis does show, even though people think that, you know, because 12 is a greater number than 10, that it's ultimately going to be best. But when you look at the whole system as a whole and you analyze all those different parts, very often, more than you think, we will find that just due to the increase in pressure drop from an E11 to an E12 might take that out of the life cycle cost range to where it's not necessarily the optimal solution. So that's why in this case, the E11 was recommended more so than the E12.
Thank you both. I have a question here going back when we showed the various service available about how should people go about to do a CAM lab test. So the specific question was, is it available in the Middle East? But maybe more generally, we could look at where is it available and how do people, who should they contact if they're interested in doing a study like that?
Yeah, well, we have actually on a global scale, we have now, if I'm not wrong, we have now two trailers in America, North America. We have one in South America. We have one in the Middle East. We have two in Europe. So these locations, you can easily ask the availability. Now, of course, we don't have 50 container labs like that standing in a garage somewhere to wait for someone to call us. So of course we try to have them out there as much as possible. And as far as I know, most of these are booked like at least 6 months in advance, because also, as was said by Jeremy, we consider also a minimum time to have them on site to be around 3 months as a minimum, and preferably actually up to 6 months on a specific site. So.
Thank you. I have an interesting question here as well on what is your impression or recommendation on online washing? Do they really clean the compressor and decrease the fouling? And how does this compare to air filtration solution?
Well, yeah, I like this question because in principle, online washing is what I always say is like a medicine, right? It's you allow your engine to get sick, and you just give it some medicine to try and keep it running a little bit better for a prolonged period of time. But in the end, it's just still getting sicker and sicker and sicker over time. So online washing is just like a delaying effect on the overall performance degradation that you will see on your gas turbine. Whereas air filtration is really the solution, because there you really avoid the engine to get sick overall. So you really keep it healthy, running efficiently at all times, and you don't even need to do all these washings, which is also at some point also a cost and also a risk factor in the end. So.
Thank you. I have one question that's a little bit more specific here, but maybe we can take a more general approach to answering it. So a customer is asking about a GT26 gas turbine with a 3-stage filter from a competitor, G4 M6, and a final E10 filter in 330 millimeter depth. And he got a problem where the final filter life was only 6 months. And he's saying what could be like various strategy to increase the life of the final filter. What the first idea that come to mind if you want to increase is life cycle.
Yeah, of course. I think here again, it's a life cycle cost analysis will give a very good comparison to show to the customer there what is really going to be the most beneficial for him to extend the final filter life. This could be different ways to do it. Either you could say, well, maybe I need to protect it with a higher efficiency initially. So instead of a G4 M6 in front, maybe I need to have a M7 or an F8 filtration in front of the E10, which will definitely extend the final filter life. The other way, of course, is trying to use a filter E10 which has a higher dust holding capacity. So instead of a 330 millimeter depth one, go to a deeper one like our 3D600, for example, without having to change the pre-filtration. But again, this is the kind of things that we can assess, simulate within our LCC powered analysis to show them really what would be the most beneficial. And we have seen actually in real life that we have moved in some cases even from 3-stage systems to 2-stage systems without needing to shorten life on any of the stages, so actually extending the life on both stages. So.
Yeah, so I'll jump in too, and we also want to really take a look at what is the particulate that is loading that final filter. So, you know, as we talk about efficiencies and particle size and capture rates, things like that, we really want to know what the concentration of that filter is. So say it's a sticky hydrocarbon, and yeah, though it's being captured, it's just loading up at a much faster rate just due to its concentration. So really want to take a look at exactly what that is being captured in the filter. So getting them sent in and have them analyzed, or doing a on-site analysis would be extremely beneficial as well.
Yeah, correct. Yeah.
And a more general question on the process that we're just looking at. How long does that process usually take, and how early should people start, either before they start a new project or before a filter change to start looking into realizing this process?
Yeah, well, again, here I'm referring back to the case study that we saw there during the project phase of the LNG terminal, way before even there was a plant built there, trying to assess the environment from day one. That's of course ideal, because then you really are going to assess what am I going to need to protect my gas turbine from in the long run, and how can I do that in the best way forward. Now, of course, I imagine in a lot of projects, people or already in an advanced stage in a project, so then of course the timeline will be shorter. But ideally, yes, as soon as possible within when you have the idea of a new project, a new power plant to be built, or an offshore project, whatever, try to make the assessment as early as possible, so you can write your specification based on pure performance criteria and submit that to the EPC contractors and the OEMs, so that in principle you will always get the performance that you want, and you will not be put in a situation where you think you have written a specification that is going to deliver, but in reality it's not really going to deliver what you expect. So, and also there we can help on writing that kind of specifications, or drive that specifications to a more performance-driven spec for sure.
Thank you. You've talked a lot about multi-stage filtration and the advantage of being able to choose various filtration solutions. Are they the same kind of option with people having pulse filter? And when it comes to pulse filter, what can people do to kind of improve their life cycle costs? Are there solutions available as is? Is it typically retrofits? Can you talk just a bit more on for people in a region of the world that are pulse filter?
For the
Yeah.
Go ahead, Jordan.
No, go ahead. Go ahead.
I was going to say, for the vast majority of pulse systems that are installed globally, they're a single stage pulse. So you're very limited to what the strategy is to do any improvements. The easiest part is to look at the actual filter element themselves, but there are some ways that we can very easily retrofit by adding a static high efficiency filter stage downstream of the pulse system with minor adjustment to the duct run. So it is very easy, and determining what that best solution is key to what efficiencies we're trying to achieve.
Thank you. Now we probably have time for one more question. I have a quick one here. You've presented a map early in the webinar where there was a lot of information on environmental data. Is this available for customer, or how can people get an assessment of their site based on this information?
All of our sales team globally has access to the environmental map. It is one of our newest innovative tools that we use. We're currently looking at an option that could be online for the public, but at this time, it's best to just contact your local Camfil office.
Yeah, and in general, we just need the coordinates of the location where you're situated, or where you plan to have your new project, and we can have this benchmark overview at that point already. But as suggested, for a new project, yes, the recommendation would still be to make a more local long-term analysis to make sure you understand your environment in detail, and you know exactly how you should protect your gas turbine with filtration solutions. So.
Thank you. I think that is about the end of our the time we had allowed for the question. While we do our closing, please feel free to keep typing in any question. I see a few that we haven't had a chance to answer. We will do that by email. We will contact you afterwards, after this webinar. For accessing previous webinar for part 1 and 2, we've mentioned this a few times during the webinar. You can access them on our YouTube channel or on our Camfil website. You'll see the top 4 enemies of gas turbine or the value rating available there, as well as more contents from previous series. You can follow us on LinkedIn if you want to be the first one to know about new webinars coming up. We have a few product launch that will be advertised pretty soon, coming in for the fall with interesting services like online monitoring and new filter product as well. So as we close this webinar here, you will have a pop-up for a little survey. We really appreciate your feedback, and if you have any interest into further subject, things that you would like us to touch next, please feel free to type in it in the survey. We're always really interested by that. And otherwise, you will receive the link to this recording within 24 hours if you want to share this with colleagues, or if there's part that you missed due to other commitment. Thank you again for joining us, and we look forward to see you next time on our next webinar. Bye.
Thank you. Thank you, everyone.
Thank you.